Hello friends, last class we studied about radius of gyration. Now today we are going to learn about torque and moment of inertia. What is the relation between torque and moment of inertia? That torque is equal to I alpha. So let us derive that relation. So as seen in the diagram you can see this is any rigid body M1, M2, M3 are the masses of 8, R1, R2, R3 are the perpendicular distances from the axis of rotation, and the body has angular acceleration alpha. Again I repeat, alpha is the angular acceleration. See, whenever there is a force, there is a acceleration. F is equal to ma. So whenever there is a torque, there is an angular acceleration. So we say that the body accelerates linearly under the action of the force, while the body exhibits angular acceleration under the action of the torque. Okay, so see, as I had mentioned you earlier also, the alpha, that is the angular velocity, is common, but since their linear velocities v1, v2, v3 are different, their linear accelerations are also different. So a1, a2, a3 up to an are their linear accelerations, but remember it, the relation linear acceleration a is equal to r alpha, linear velocity v is equal to r omega, omega angular velocity, alpha angular acceleration. So in this formula alpha is going to remain same, because as a whole the body is accelerating with one common angular acceleration, but each particle may have different linear accelerations. So we have a1, a2 up to an. These are the linear accelerations, and the relation between them, a1 is equal to r1 alpha, a2 is equal to r2 alpha, and so on. Now we know the basic equation as per the Newton's law. F1 is equal to m1 a1. Substitute the value of a1 as r1 alpha. So F1 is equal to m1 r1 alpha, and so on. So what is the moment of force or the torque? Moment of force is nothing but torque, and we know that torque is equal to F cross R, force into perpendicular distance. So here r cross f, rf sin theta, theta is 90. So sin 90 is 1. So the moment of force or torque is F1 R1 on particle 1. Now substitute the value of F1. So F1 is equal to m1 R1 alpha into R1. R1 into R1 will give you R1 square. In the same way, for other particles, it will be m2 r2 square alpha, m3 r3 square alpha, and so on. So the total torque acting on the body will be m1 r1 square alpha plus m2 r2 square alpha, and so on, m1 rn square alpha. Take alpha common, right? So we know it, m1 r1 square plus m2 r2 square up to mn rn square is nothing but moment of inertia. So my equation, the relation between torque is equal to I alpha. This resembles the equation F is equal to ma in linear motion. Whatever role played by force in linear motion, the same role is played by torque in angular motion. Mass in linear motion, moment of inertia in angular motion. Acceleration, linear acceleration A, angular acceleration alpha. So the analog of F is equal to ma equation in linear motion is nothing but torque is equal to I alpha in rotational motion. So this is the relation between torque and moment of inertia. I hope guys you have understood it. Now let us go ahead. So angular momentum and moment of inertia. See, we know what is linear momentum. Linear momentum P is equal to mv. Same way we have angular momentum L is equal to I omega. Angular momentum, the relation between L is angular momentum, I moment of inertia, omega angular velocity, P linear momentum, m mass, v linear velocity. So the analog of P is equal to mv equation in rotational motion is L is equal to I omega. Now see this diagram, we are going to derive this relation that L is equal to I omega. So here again the same diagram, m1, m2, m3 are the particles, r1, r2, r3 are the perpendicular distance from the axis of rotation, and the body is having angular velocity omega, uniform angular velocity omega. So we know this relation between, I told you previously also, v is equal to r omega. Relation this we had done it in circular motion if you are remembering. So v1 is equal to r1 omega, v2 is equal to r2 omega, v3 is equal to r3 omega, and so on. See, these relations are very easy. Linear velocity r into angular velocity. Linear acceleration a, r into angular acceleration. A is equal to r alpha. V is equal to r omega. Torque is equal to r cross f. Angular momentum L is equal to r cross p. Here these are the v1 r omega. We know the linear momentum p1 is equal to m1 v1. Substitute the value of v1 as r1 omega, so it is m1 r1 omega, and as I told, angular momentum is r cross p, but p is m1 r1 omega into r1, so this will give you m1 r1 square omega. In the same way, for other particles it will be m2 r2 square omega, m3 r3 square omega, and so on. So the total angular momentum of this n number of particles, L1 plus L2 up to Ln, that is m1 r1 square omega plus m2 r2 square omega up to mn rn square omega. Omega is constant, take out that common, so 1